So in this lesson we're going to talk about two things. We'll first introduce the Euler equations, which are a practical example of a system of coupled hyperbolic equations. And then we'll also introduce flux limiters, which are useful for representing the convection term in conservation laws. So the Euler equations represent inviscid fluid flow and are represented by the mass, momentum, and energy equations. Here the equations are written in one dimension, and we have here mass, momentum, and energy written in non-conservation form. And then on the right, if we make use of the substantial or material derivative, we can see the representation in terms of a Lagrangian-like formulation where we're following the flow. The first thing we want to do to work with the Euler equations is to just rewrite the energy equation in terms of pressure. The easiest way to do this is to take the ideal gas law, where we define pressure as P equals rho RT, and then if we take the derivative with respect to that, then we get this dP dt is RT d rho dt plus rho r dt dt, and we can rewrite the temperature with respect to time in terms of the energy. Then if we use these identities where we can represent the universal gas constant and constant volume heat capacity in terms of gamma, where gamma is the ratio of specific heats, then we can represent these equations, or we can use this representation and insert these quantities into the mass and energy balances. So where we have d rho dt, up above we have an equation for that, and where we have dE dt, we have that same equation. So if we just insert into the definition of the derivative of the ideal gas law, then we end up with the following progression. dP dt equals this right hand side, and then we can split that using the definition of the substantial derivative, and then simplify. We get a cancellation of two terms, and then we can pull another term to the left hand side of the equation. And so we've effectively replaced our energy equation with this pressure equation, so that we get the following equations for mass, momentum, and energy. Now we can write these equations in vector form if we write U as just a vector of density, velocity, and pressure, and then this coefficient matrix A, which consists of U, density, pressure, and the ratio of specific heats, in the form du dt plus AU du dx. So right away it looks like our favorite hyperbolic equation, the 1D wave equation. Of course, this is a coupled system of equations. And so we have this matrix A, which is going to result in several terms with respect to x. We can decouple the system by diagonalizing it, and we've seen several times how we can do that. We just take Ax equals lambda x, where x here would be an eigenvector and lambda is an eigenvalue. And if we collect all the eigenvalues and eigenvectors together, we can write AV equals V lambda. Then multiplying by, on the left, by V inverse, we get V inverse AV equals this lambda, or A equals V inverse lambda V. So I guess we're multiplying on the right by V inverse, where lambda is a diagonal matrix of the eigenvalues. Here, the columns of the V matrix are would be the eigenvectors of A, and the corresponding eigenvalues are on the diagonal of this diagonal matrix, capital lambda. So if we take our system of equations here, du dt plus A du dx, and we multiply through by the inverse of V, then we can represent this system as V inverse du dt plus lambda V inverse du dx. If we assume, for argument's sake, that the V matrix is a constant, then we can pull it inside the derivative, and we can see the decoupled system looks identical to our 1D wave equation. So we have, for instance, for the first component of u hat, we have d u hat 1 dt plus lambda 1 times d u hat 1 dx, that should be an x there, equals 0. And it's basically a system of three uncoupled one-dimensional wave equations, which we're used to analyzing. So we can see that most of the things that we're discussing for the toy problems carry over nicely if we change the basis of our system. Now, in this setup, we can see that the lambda here, each lambda I for the components represents the wave speed in the transformed system, and we can evaluate those eigenvalues if we take the determinant of a lambda minus I. I'm sorry, this should be a minus lambda times the identity matrix. So if we set that equal to 0 and solve for the determinant, then we get the following polynomial, which we can solve directly for the eigenvalues. So we have lambda equals u plus c, and lambda equals u minus c. Those would be the three eigenvalues of the system. Here c is the speed of sound, and the Euler equation wave speeds are the convection velocity and the convection velocity plus and minus the sound speed. In many flows, we have the sound speed being much, much faster than the convection velocity, and that results in a stiff system of equations. So this is just a good example of a system of equations that we see often in engineering practice. The Euler equations are a model for flows where we're able to neglect viscosity. They occur in boundary layer-like flows outside of the boundary layer, for instance, and we can use them in acoustics and other sorts of applications. And so it lets us see both an example of a system of hyperbolic equations that's practical, and also lets us nicely look at how we can use techniques that we've seen before in terms of diagonalizing matrices to reduce a coupled system of equations down to a system that is decoupled and then can be analyzed more simply in the revised basis. So that's where we'll stop with this particular part of the discussion. And then the second portion of the discussion concerns the flux limiters. So we'll transition over to the flux limiters now. If we consider a conservation law, such as du dt equals minus a du dx, here a would be the wave speed, and u would be our unknown that we're trying to solve for. We can rewrite this more generally if we write du dt equals minus df dx, where f is a flux. Here we're going to take f to just be the wave speed times the velocity, and we'll treat the wave speed as a constant, but in general that's not a requirement of the methods that are involved. And we'll look at the following schematic. So in this picture we have three grid cells, a W cell, a P cell, which we'll call cell I, or the base cell that we're interested in, and the E cell. The initial profile is this thick black line, okay, where we have basically a square wave, and the velocity is such that the wave will be moving to the right. The filled black circles represent the value of u in the three volumes. And then we have at the faces of this P cell, we have a west face and an east face, and we have these open squares that represent the value of u at the faces, where here we're taking the value at the face to be the average between the neighboring two cells. So here the square face value will be just the same as its neighbors because the neighbors are the same. Whereas on the east face, the black or the open square will be midway between its two neighbors. When we go to take a time step, what we expect to have happen, the exact solution, is simply that this square wave will simply move to the right. The whole profile will just convect to the right in time. We'll have the same profile shifted. If we look at what happens with the numerical method, however, that's not exactly what we see. The initial profile indicates that there should be no net accumulation in the P cell because we expect to have the velocity, if it's just transitioning to the right, we expect the value of this black cell here to remain constant, this black circle to be constant. But if we look at it from the point of view of what's the flux in minus the flux out, we can see that the flux on the west face is going to be higher because that flux is at the open square here at a higher value than the flux leaving the cell down lower. And so here I've indicated that by these shaded red regions, which would be the amount of material over a time step that moves to the right due to the west flux versus the amount of material that leaves due to the east flux. You can see that the flux leaving is less than the amount entering, and the result is going to be that we actually increase the amount, the value of U in the P cell. So what started as just a flat wave coming flat and then dropping down to a new value has now gone flat and then increases and then drops down. So we've generated some oscillation just by having a difference in the way that we're evaluating the fluxes. And we can see that here. Flux on the east face is the average of the two cells and also for the west face, but because UP and UE are lower than UP plus UW, we end up with a higher flux in than out. And that gives us that oscillation that we've seen when we use standard kinds of flux descriptions in terms of the average of the two neighboring cells, which is the most obvious thing to do. If we implement such a model, here again we've seen this before. Here we have our initial condition is the blue line with symbols, and we're running this for one flow through time. And here we're just comparing three different methods. So we have the exact solution, and then the green line is the upwind scheme applied with an explicit Euler like time advancement. The red line is a second order upwind, and the cyan line is a Lax-Wendroff approximation. And you can see that the upwind scheme doesn't have any oscillations in it, but it's also very diffusive and it's a low order method. The two higher order methods, second order in space, are the second order upwind and the Lax-Wendroff method, and both of those have this problem with oscillations that's causing us so much grief. Of central importance to the description is Godunov's theorem, and he said that linear numerical schemes for solving partial differential equations have the property of not generating new extrema, can be at most first order accurate. So this is from Wikipedia and it shows up in lots of textbooks. Basically it's saying that if you have a linear numerical scheme like a central difference or averaging the two neighbors or using an upwind method, those can only be first order accurate if they don't generate oscillations. So in terms of this picture, the upwind was first order accurate, it didn't have oscillations. But the linear methods like Lax-Wendroff do have these oscillations that happen. What this means that if you want to avoid the wiggles, you either have to use a first order method or you have to use a nonlinear scheme. And so that's what we're going to look at with the flux limiters, is what those nonlinear schemes look like. Flux limiters limit the flux, as the name indicates, to avoid the kind of oscillation that we saw. So if we scroll up, we saw that the flux here was too high, or conversely the flux here was too low, and that's what resulted in this oscillation. We got this too much mass going into the cell. For flux limiters, we can consider a simple time integration, like an explicit Euler time integration, or we can build it up as we would in a Runge-Kutta-like method, but here this is just written for a simple time integration. And we can evaluate, what we need to do is be able to evaluate the flux on the east face and the flux on the west face. So we just take our original PDE, and if we integrate that over the control volume and evaluate the time in an explicit fashion, we get UIN plus 1 is UIN, minus delta t over delta x times the flux on the east minus the flux on the west. So what we're going to do is evaluate the flux on the faces, and here we'll just consider the east face, as a combination of two kinds of fluxes. We'll call Fe superscript L a low order flux, and we'll call Fe superscript H a high order flux. So this could be like an upwind method, and maybe for the low order method, and maybe an average of two cell quantities like u plus u over 2 times the velocity like we saw above for the high order flux. So it's just a combination, and then we have this function phi of r, which is a number that basically does the interpolation, some kind of an interpolation between the low order flux and the high order flux in order to find the actual flux that we're going to use in the face. So all of this is about find the fluxes, the in versus out terms, and we can use a combination of a low order flux like upwind, which doesn't have any oscillation, and we can use we can combine that with a high order flux that does have oscillation, and our goal is to make a flux that is both high order and doesn't have any oscillations. So that's what we're trying to do. So basically the method is as it looks on the screen, and all we have to do here is define what we're going to have for phi e. And if we define phi e, then we're done. So here we have phi r is the flux limiter function, and it's a function of r, and r is given by this quantity here. It's basically just the ratio of successive slopes. So if you take ui plus 1, and ui minus 1, then this is basically just the ratio of the difference between the two neighbors and the two neighbors next door to it. ui minus 1 divided by ui plus 1 minus ui. So r just gives you an indication of how smooth your solution is at the given point. So if r is 1, then you basically don't have any change in the slope of your problem, and you have a very smooth solution. And when you have a smooth solution, you can use a high order flux without getting oscillations. And we saw that the oscillations happened in regions where the solution wasn't very smooth. So here r would be like the ratio here, this difference divided by this difference, or this difference divided by this difference. And when there's no difference, it's smooth, and you can use a high order method. When there's a big difference, you want to use the lower order method. So we just evaluate this ratio of successive slopes. When r is 1, it's smooth. If r is 0, then there's a large change in the profile, and we would want phi to be equal to 0 so that we use a low order flux. And we can see that up here. So if we write this as phi, when r is 1, we would want phi to be equal to 1, and when that happens, it's smooth, and Fe cancels, leaving Fe high order. We're using a higher order flux. When phi is 0, when we have r is 0, we want phi to be 0. In that case, we go to the lower order flux, and that's all there is to it. Now, I didn't mention that if we use upwind for the low order method and a central difference, or rather averaging the two neighbors to find the high order method, then this equation here can be rewritten as follows, where Fe1 would be an upwind flux and Fe2 would be a downwind flux. Phi is still the same function, and so you can rewrite it in a little bit different form. And so you can see that when phi is 0, you get the upwind value, and when phi is 1, you get a central difference, and when phi is 2, you get the downwind. So it's kind of like interpolating between upwind, downwind, or central difference. Or not central difference, but yeah, it'd be a central kind of equal weighting between the two sides of the fluxes. Okay, so phi r, we're not going to go into the derivation of how phi r is computed. See if we can get that to fix. There it goes. Just exit out of here. So we're not going to go into the details of how this function phi is computed, but the following graph shows that functions that are second order and also have the property of not generating any oscillations are going to be functions that pass through the blue region. Okay, so we call that a TVD scheme, total variation diminishing. That basically means if you have oscillations, you're not making them grow. If you don't have oscillations, you won't create any. So total variation diminishing. And any function that goes through this blue region is going to be a valid flux limiter that we can use. Okay. There's lots of possibilities for flux limiters. Wikipedia gives a whole bunch of examples, and here you can see a whole bunch. There's the charm, and there's min mod, and there's super B, and there's Van Leer, and there are muscle type schemes, and a number of others. Here we'll consider the super B limiter, the Van Leer limiter, and the mid mod limiter, and also we'll look at a muscle approach. And this is just running this through a simple 1D wave equation. These first four schemes at the top are super B, Van Leer, min mod, and muscle. And then for comparison, we're going to compare that to the first order upwind and a second order upwind method. And so these were shown previously where we get very diffusive, and also second order shows these oscillations. This particular case uses 200 grid points, and we're using a CFL of 0.4, and I think we're using a third order Runge-Kutta method to integrate the system. We have periodic boundaries, and we're running it for a single flow through time. And you can see the behavior of these flux limited methods is much, much better. We don't get any oscillations, and generally the fidelity is much cleaner than we get with these other methods. The upwind is very diffuse, and so we've gotten rid of that with these higher order schemes. The second order upwind works pretty well if it weren't for the oscillations, and so we can see these other methods also don't have the oscillation problem. Super B arguably does maybe the best, although it tends to make the peaks squarish. So if you get high peaked regions, they kind of get squared off. And so which method you choose depends a little bit on the problem type you have, and it's pretty easy to change methods. You literally just code a one-liner in your code will change the function that you evaluate, and you can go on with those. So these are really popular to use in all kinds of CFD applications where we have convective terms in the equations, and we'll often evaluate the fluxes using these high order flux limited schemes. I'll just mention another class of schemes that we aren't going to talk explicitly about here in terms of examples and showing the method, but they're ENO schemes and WENO schemes. This means essentially non-oscillatory method, and then there's the weighted, essentially non-oscillatory method. That would be a WENO scheme. And those come in different orders. A fifth order WENO is pretty popular. And there it does a similar kind of thing where you'd have different stencils, and those stencils might be centered, or they can be weighted to one side or the other. And we've seen how to make one-sided approximations using Taylor series. The WENO methods use polynomial approximations where the points of interest are on one side, the points that are used to build up the polynomial at a given point are on one side or the other, or centered. and then you do weightings among those different polynomials in order to decide what the best approximation is, depending again on the local characteristic of the profiles. So that's an intro to flux limiters. It's a little bit more complicated to use them and understand them than it was for the simple methods that we described before, but they're important and they're very practical. And so this humble looking PDE that has a very trivial analytic solution is numerically quite challenging, and is something that's taken a lot of work and a lot of research. And we'll stop there. Please let me know if you have questions.